Design of a lexical analyzer generator. Lex. Lex is a tool that allows one to specify a lexical analyzer by specifying regular expressions to describe patterns for tokens. The input notation for the Lex tool is referred to as the Lex language, and the tool itself is the Lex compiler. So how does the Lex work? We assume that we have a specification of a lexical analyzer of the form p sub 1, action sub 1, up to p sub n, action sub n, where p sub I is a regular expression and action sub I is a program fragment to be executed whenever a lexeme matched by p sub I is found in the input. Here's a model of a Lex compiler. In this figure, we'll see that the Lex compiler constructs a transition table for a finite automaton from the regular patterns in the Lex specification. The lexical analyzer generated by the Lex compiler has an input buffer with 2 points to it, a lexeme beginning, and a forward pointer. This lexical analyzer consists of a finite automaton simulator that uses the constructed transition table to look for the regular expression patterns in the input buffer. One method for pattern matching is to construct a transition table of a non-deterministic finite automaton for the given patterns. We'll do that by first constructing an NFA and P sub I for each pattern P sub I. So we know that P sub I is a regular expression, and based on our previous learnings, we should know how to convert a regular expression to an NFA. Next, we'll add a new start state, S sub 0, linking the start states of each NFA machines with an empty transition. In simulating the combined NFA, we'll see that there's an accepting state for each machine. While reading the input, even if we find a set of states that contains an accepting state, to find the longest match, we must continue the simulation of the NFA until it reaches termination. That is, a set of states which there are no transitions on the current input symbol. Suppose we have a Lex program consisting of 3 regular expressions. As we said earlier, we'll construct an NFA for each pattern. So here's the machine for the pattern A, for the second pattern ABB, and the third pattern A star B plus. We add a new start state, make an E transition for each NFA, then we'll have this combined NFA. For example, we have a string input AABA. So we have 0, 1, 3, and 7 as the initial states. For the input A, we have a transition from state 1 to 2, 3 to 4, and 7 back to itself. State 2 is an accepting state already. But to find the longest match, we'll continue simulating the NFA. State 7 will go back to itself after an input A, then to 8 with the next input B. After that, there will be no transition for an input A, so that's when we terminate the simulation. Given that, we have the lexeme AAB matched with the third pattern. So that's how you do a pattern matching based on NFAs.